Welcome. In this video, we are going to talk about how double integration of no integrand can represent area. So the area of some closed bounded region R. So we've got an X and Y set of bounds. And when we have no integrand or just the value 1 in here, then integrating that with both respect to X and Y provides us with an area. Let's do an example. For this example, we're going to find the area of the region R, which is bounded by the functions y equals x and y equals x squared in quadrant 1. The first thing we always want to do when we're dealing with these regions is to sketch the region. So the line y equals x, that's the identity, that's a diagonal line, and we're only going to draw it in first quadrant since that's been specified. And then we've got the line y equals x squared, which gives us a parabola. And we will find that these two values intersect at 1, 1. That's my ordered pair there. So we want to find the area of this region. Now, formerly in Calculus 1, if we wanted to find that area, we would say the integral of the top minus the integral of the bottom from 0 to 1. But we're going to set it up a little bit differently using a double integral to find area. So in this case, we'll say that area is the integral. Now, it is really just a matter of opinion how you want to integrate. In this situation, either subtracting or having my upper and lower horizontally versus my upper and lower vertically, it's going to make the, I'll get the same value for the area. And since I already have my functions y in terms of x, I'm going to integrate x first. So my x bounds go from 0 to 1. Those represent x's. And then I'll have my integral from, or for my y values, we're going to have the upper bound is x and the lower bound is x squared. Now, if we integrate this, this would be dy dx. So the first thing we will do is integrate 1 with respect to y, and that gives us a equals the integral from x equals 0, x equals 1 of y. We need to evaluate that from y equals x to y equals x squared, and then we will integrate again with respect to x. So if I set this up, that's going to be area from x equals 0 to 1. I plug in x. For y, I've got x minus, if I plug in x squared, for my y, I've got x minus x squared integrated with respect to x. So now, if we tried to set this up using a single integral from Calc 1, this is what we would have learned. So we're just kind of redefining how we can use double integrals to calculate area. At this point, this should be very easy for us to integrate. I have x squared over 2 minus x cubed over 3. We're going to plug in 1 and 0. Of course, when I plug in 0, that's going to 0 out. So we're just going to end up with 1 squared over 2, or 1/2, minus 1 cubed over 3, 1/3. 1/2 minus 1/3 gives us 1/6, and that represents the area of this region. Let's do one more area example. So for this example, we're going to find the area of some region R bounded by these 3 lines and a curve. So obviously, first step, we want to visualize our region. So the first thing we have here, we've got this line y equals 2. I'm gonna come up here. Y equals 2, I don't need to draw that dotted, is a horizontal line. We also have the line y equals negative x plus 1, so that's a y-intercept of positive 1 and a slope negative 1. So we've got that line with a slope of negative 1 passing through the y-intercept. Yep, we've got that there. And then y equals e to the x, that's an exponential curve, which has a y-intercept of 0, 1. So there we've got y equals e to the x. We got y equals 1 minus x. So we want this region enclosed by these three curves. That's by region R in here. So if we tried to set this up using our Calculus 1 knowledge, we have different upper and lower bounds. So we'd have to use two integrals anyway, because we have to say, well, one integral from negative 1 to 0 to minus the quantity 1 minus x, and then plus another integral from 0 to 1 from 2 minus the function e to the x. So we're just going to set this up our new Calc 3 double integral way. And I have choices. Now, I obviously don't want to pick them vertically because that's not, I'll still have to split it up. So if I choose these horizontally, then I could choose a left and a right to be my upper and lower bounds. Now, if we're setting it up that way, we need our functions in terms of y. We need x in terms of y. So for example, y equals e to the x, that's the same as x equals the natural log of y. And y equals 1 minus x, that's the same as x equals 1 minus y. So if I want to calculate the area, I'll set this up. I'm going to say that my y values here are between 1 and 2. So my first integral, I've got y equals 1, y equals 2. And then my second integral, my lower bound, is x equals 1 minus y. My upper bound is x equals the natural log of y. And then, of course, we want to integrate this, dx dy. I choose dx because my first bounds are x in terms of y, and then dy, my second bounds constants, those are y's. So the main thing we want to think about here is we chose that upper and lower bounds for my x horizontally. So those were x's. They're bounded by functions, so I need each of those functions x in terms of y. So if you're unsure, I just want to encourage you, pause, think about it right now. Make sure this makes sense to you, how I'm setting it up. All right, so at this point, though, the integration should be very easy. These are my y values from 1 to 2. When I integrate 1, I'm going to get x, and that's from x equals the natural log of y to x equals 1 minus y. I will still need to integrate with respect to y once I'm done, because the y is still there. Once I plug these two functions in, this will be a function of y values. So that gives me from 1 to 2, I have ln y minus the quantity 1 minus y, or the integral from 1 to 2 of natural log of y minus 1 plus y. We can integrate each of these terms pretty easily. Now, the integral of natural log y, we should know that from Calc 1. That is y natural log of y minus y. All right, so the integral of natural log of y, that's a formula that we use here. Then we've got minus 1, that will be minus y, and plus that y, that is plus y squared over 2, and we'll need to evaluate from 2 to 1. So obviously those two y's in the middle, I can simplify that and get negative 2y plus 1/2 y squared. From 2 to 1, at this point we just plug in. So plugging in my 2, I've got 2 natural log of 2 minus 2 times 2 plus 1/2 times 2 squared. Plugging in 1, I'm going to have minus all of this. I've got 1 natural log of 1 minus 2 times 1 plus 1/2 times 1 squared, which I have 2 natural log of 2 minus 4. 4 or 2 squared is 4 divided by 2 times 1/2 gives us plus 2. The natural log of 1 is 0, so I've got minus 0 minus negative 2 plus 2, and then minus 1/2. And negative 4 plus 2, those cancel. The 0 is gone. I have 2 natural log of 2 minus 1/2. That's fine as my answer. Just to show you, we have a property of logs. I can put that up here and say 2 squared. So I'll simplify this a little bit and say natural log of 4 minus 1/2. And that's my final answer. So this one using Calc 1, we definitely would have still had to set up 2 integrals in order to calculate it. It's just a different way of setting it up. I think this notation is a little bit more simplistic. As long as you can calculate the integral and find the area bounded by those curves, it's going to be helpful. And, as there are more curves and this becomes more complex, this newer notation is really going to help us the most. As always, email me if you have any questions.